All right, so today we're going to look at rules of exponents involving radicals. All right, we're going to go ahead and look at the rules of exponents that you guys studied yesterday in your prerequisite work, starting with the product rule. If I have a raised to the nth power times a to the nth power, notice both bases are a. When I am multiplying, I simply add those exponents together. Notice the base does not change. So 2 squared times 2 cubed is 2 to the 5th. And if I was to write this out the long ways, 2 squared is 2 times 2. 2 cubed is 2 times 2 times 2. And there's a total of 5 2's, which is really 2 raised to the 5th again. Our next rule is our quotient rule of exponents. And so if I have a base a raised to the nth power divided by base a raised to the nth power, notice again, both bases are the same. We are going to, when dividing, subtract the exponents. So if I have 2 cubed over 2 squared, I can, since both bases are base 2, I can simply subtract the exponents, 3 minus 2, and it would be 2 raised to the first, which is 2. And if I was to write this out the long ways, 2 cubed, 2 times 2 times 2, 2 squared, 2 times 2, I can cancel two 2's from both the top and the bottom of this fraction, and I'm left with, again, 2. Our third rule of exponents is our power rule, which simply states if I have a base a raised to the power of m raised to a second power of n, so a power raised to a power, we're going to go ahead and multiply those exponents or powers together. So a to the mth raised to the nth is really a to the m times n. So in this example, 2 cubed raised to the third, I can multiply those together, 3 times 3. Again, the base stays as 2, so my answer is 2 to the 9th. Writing it out the long ways, 2 cubed is 2 times 2 times 2, and then I'm cubing it, so multiplying it by itself 3 times. You'll notice there's 9 total 2's that I'm multiplying together. Again, 2 to the 9th. And then we have our inverse rule of exponents, which simply states if I have a negative exponent, I can take the base of that negative exponent and make it the reciprocal to make it positive. So a to the negative first is really 1 over a to the first, or 1 over a. So if the negative exponent's in the numerator, you bring it down to make it positive. If my negative exponent was in the denominator, I can bring it up and make it positive by putting it up in my numerator. I'm basically just taking the reciprocal. So 2 to the negative first would be really 1 over 2 to the first, or 1/2. So that is our negative rule, or our inverse rule of exponents. And then finally, number 5 is our zero exponent rule, which says that any base raised to the power of 0 is 1. And now let's talk about why that is. We know that 5 squared is 25, and if I take 5 squared in my denominator, 5 squared over 5 squared is 25 over 25, which again is 1. And using our quotient rule, I know I can take the bases of 5 and subtract those exponents, since this is division, and I get 5 to the 0, which has to equal 1. So by definition, anything to the 0 power has to be 1. So in this example here, I have 2 to the 0. Again, base is raised to the 0 power. My answer is 1. All right, let's go ahead and look at some practice problems to do as a warm-up. So take a few minutes and pause this video, and I want you to try these 6 problems. All right, looking at number 1, we have x cubed times x to the 5th times x, or x to the 1st. Since we are multiplying and all the bases are the same, they're all x, I can go ahead and add those exponents together, 3 plus 5 plus 1, and I get x to the 9th as my final answer. Number 2, I have x to the 12th divided by x to the 5th. Both bases are x, and with division we subtract, so 12 minus 5. I get x to the 7th power. Number 3, I have x squared raised to the 4th. So we have an exponent raised to an exponent, or a power raised to a power. We multiply those exponents together, and I get x to the 8th. Number 4, 7x to the negative 9th, y to the 4th. This is really saying 7 times x to the negative 9 times y to the 4th. And again, I see I have a negative exponent. And you guys know we can't leave a negative exponent in our final answer. It's not considered simplified. So I'm going to take this x to the negative 9th and make it the reciprocal. So it's 7 times 1 over x to the 9th times y to the 4th. So if I made all these fractions, on top I have 7 times 1 times y to the 4th, which is 7y to the 4th. And on bottom I have 1 times x to the 9th times 1, which is just x to the 9th. So final answer, 7y to the 4th over x to the 9th. So again, notice that I only took the factor x to the negative 9th and made the reciprocal of that, since that was the only part in this problem that had a negative exponent. All right, looking at number 5, I have 2x to the 5th raised to the 4th. So now I have to take each thing in this parentheses and raise it to the power of 4. So I have 2 to the 4th, and then x to the 5th times 4. Notice that's exponent to exponent again, or power to power, times 2x to the 6th. So 2 to the 4th is 16. 5 times 4 is x to the 20th, times 2x to the 6th. And I can multiply my coefficients together. 16 times 2 is 32. I have the same bases, and they're being multiplied, so I'm going to add those exponents. 20 plus 6 is 26. So 32x to the 26th. And then finally, number 6, I have 30 over 3. We can go ahead and reduce that down to 10. Make sure I put the 10 on top. I have x to the negative 7th. I need to make that a positive exponent, so I'm going to bring that down by taking the reciprocal. I have x to the negative 3rd on bottom. I'm going to take the reciprocal of that to make it a positive exponent. So x cubed is now in my numerator. Y cubed is already got a positive exponent, so we're not going to move that. And we have y to the negative 5th, which has a negative exponent, so we'll take the reciprocal by moving it up to my numerator. And so now I have 10x cubed, y to the 5th over x to the 7th. And I can combine, since y to the cube times y to the 5th, they have the same bases, and I'm multiplying, I can add those exponents. So I have 10x cubed, y to the 8th for 3 plus 5 over x to the 7th. And then you should be able to recognize that I have x cubed on top, x to the 7th on bottom. Everything's being multiplied on top, so I can reduce those x's. And so to do that, I have x cubed on top, x to the 7th on bottom. We can subtract those, 3 minus 7. So I have 10x to the negative 4th, y to the 8th. And again, here's my negative exponent. So I'm going to take the reciprocal of that, just that part. And I get 10y to the 8th over x to the 4th. Now, what's cool about these rules of exponents is that it applies to any exponent that is considered a real number. So if you think back to our first day of class when we discussed all the different types of numbers that are in existence, we talked about real numbers and then imaginary numbers. Well, with the real numbers, remember there's irrational numbers, which are numbers that cannot be written as a fraction. So examples include pi, square root 5, square root 2. Rational numbers are numbers that can be rewritten as a ratio or a fraction. So 1/2, 0.7, which is 7 over 10, 1/9. Integers are negative numbers and positive numbers. So like -1, -2, 0, 1, 2. Whole numbers are 0, 1, 2, 3, 4. And then we have our natural numbers, which are our numbers that we can count physically. So 1, 2, 3, 4, and so forth. All of these rules of exponents apply to all these different types of numbers that could be potential exponent values. All right, so we're going to take a look at some practice problems involving these rules of exponents, specifically where the exponents can be any sort of real number that I just mentioned. So they could be rational, irrational, integers, whole numbers, natural numbers. So let's look at number 1. We have x to the root 5 times x to the 3 root 5. So notice again, both bases are x, and I'm multiplying. So when that happens, I'm going to add my exponents together. And we know that root 5 is really 1 root 5. So 1 root 5 plus 3 root 5 is x to the 4 root 5. All right. Next one, number 2. I have 2 to the 7 pi over 2 to the 4 pi. So those exponents are irrational, but the bases are both 2. and I'm dividing. So when that takes place, we keep the base the same, 2, and I subtract my exponents. 7 pi minus 4 pi would be 2 to the 3 pi. So now in example 3, I have 3x to the 2 pi raised to the third. So I have to take each of these two factors inside the parentheses and raise it to the third power. So I have 3 to the third, and then I have to take x to the 2 pi raised to the third. Well, we know 3 cubed is 3 times 3 times 3, which is 27. And then power to power, or exponent to exponent, I multiply those. So it's 2 pi times 3, and I get 27x to the 6 pi. And for number 4, we have a negative exponent, and it's x to the negative 1/2. So again, one of our rules of exponents says if I see a negative exponent, take that base and put it in this case, the denominator, since this was really the numerator of our problem. And 1 over x to the 1/2 is not considered simplified. And if you recall, I mentioned this once before in our last unit, but x to the 1/2 is really equivalent to the square root of x. And we're going to talk about this rule actually tomorrow, which is kind of the basis of section 2.1. This is going to be called our rational exponent rule. But again, we'll talk about this more tomorrow. So if I rewrote this as 1 over square root of x, we know that we have to rationalize it. And I get square root of x over x. Or I could write this as x to the 1/2 over x. So either one. And then finally, number 5, which is probably the trickiest one out of the group, we have 3 to the 4x minus 1 over 3 to the 2x minus 2, and that whole thing is being raised to the negative 2 root 3 power. So usually when I deal with these types of problems that look a little more difficult to handle because there's a lot going on, I like to refer back to my order of operations. Please excuse my dear Aunt Sally. So remember, I do parentheses first, then exponents, then multiplication, then division, then addition, finally subtraction. So since there's a parentheses in the problem, I'm going to just start by simplifying that. Notice both bases are 3. So I can go ahead and write this as base 3, and since this is dividing, I'm going to take those exponents, 4x minus 1, and subtract it to 2x minus 2. And then I'll deal with that negative 2 root 3 afterwards. So if I clean this up, I have 3 to the 4x minus 1 minus 2x plus 2, minus a negative 2 becomes a positive 2. And I'm raising that to the negative 2 root 3. Cleaning this up, we have 3 to the 4x minus 2x is 2x. Negative 1 and 2 is positive 1. And I now have to raise this to this exponent of negative 2 root 3. So at this point, I can see I have to raise this to a negative exponent. So if I want to take this base that's raised to a negative exponent, I can rewrite that negative exponent as a positive exponent by taking this whole thing as the reciprocal. So I have 1 over 3 to the 2x plus 1 raised to the 2 root 3. And I'll multiply these exponents together since it's a power to a power. And I get 2x times 2 root 3, which is 4x root 3, plus 2 root 3. So here's my final answer, 1 over 3 raised to the 4x root 3 plus 2 root 3.